Okay, guys, so for interpretation, the first kind of question that we need to ask is, does X affect Y? So is the effect of X statistically significant? Or in other words, can we reject the null hypothesis that the effects of X and Y is just because of chance or because of the way that we draw the sample of this study? And similar to what happened in the past with the t-test, I'm sorry, with the t-test and with the other significant tests, we need to examine the t-values and the p-values of our results. And remember that we want to have large t-values and degrees of freedom and very tiny or very small p-values. We want to see stars, which means that the p-value needs to be smaller than 0.05, which means that the probability that the null hypothesis is correct is less than 5%, or in 5 cases out of 100. And if we see more stars, the more stars we see, the better. Okay? Okay, so after we know that the effect is statistically significant, and let's say that in this example, income inequality has a statistically significant effect on the index of political stability. After we know that, the next question is related with the substantive significance. And the substantive significance is the question about how does X affect Y. It's not does X affect Y, but how does it? How affects Y, okay? And, okay, the first thing that we need to notice here is if the sign of the relationship is as we expected in the hypothesis. And remember that we said that income equality, or income inequality in this case, is negatively related with political stability. So we expect to see that kind of relationship. The worst thing that can happen to you, between quotation marks, is that the relationship of interest is statistically significant, but the effect is the opposite. If you have something, if you experience something like that, you need to reject your own hypothesis, which is the worst case, right? And to some extent, you need to explain why this unexpected event happened. Why, for instance, imagine that in this case, the relationship is not like this one that is negative, but is positive. So what explains that a country that is more or countries that tend to be to have higher levels of inequality tend also to be more stable? That's counterintuitive. Something happened here. Maybe there's an omitted variable, there was a problem of or a measurement error, or maybe we have something wrong in the theory. Maybe this is a puzzle that we need to solve, and we need to propose a new theory to explain this puzzling kind of event. Okay, but that's the worst case. That's what you don't want to see in your results. Okay, so the first thing is check the sign of the effect. The second part is explain the magnitude, or examine the magnitude of the effect of X on Y. And in order to do that, you need to find a way to communicate in a meaningful way this effect. Maybe you can you need to see what is the scale of your dependent variable, and trying to explain in terms of the scale of your dependent variable. And let me give you an example. So for this particular case, that is a mock example, let's say that beta sub 1 is equal to minus 0.5, right? This is a negative effect, and this means that per each increase of 1 percentage point of the Gini coefficient, there is a 0.5 decrease in the index of political stability. But because the effect is very tiny, we don't understand well if this is an important effect or not. Imagine that we don't have, if we don't have this graph, we cannot picture the effect in a meaningful way. So we can try different things. For instance, we can say, okay, if there is a huge increase in inequality, imagine that 20, for instance, 20 percentage point. So a country suddenly becomes very unequal. That country is going to suffer a decrease in 10 percentage point in political stability. So in other words, we can say that if a country becomes very unequal very suddenly or very quickly, what we can see here is that maybe there's going to be an outbreak of war or violence or these kind of things, right? That's what we are saying here. But notice that we had to find I'm sorry, a value that is meaningful in the scale of the index of political stability. Okay. Another way to do it is to work or to play around the concepts of the mean and the standard deviations and the of both your dependent and independent variable. Okay. So let's say this is artificial data. Let's say that the mean of the Gini coefficient is 40%. Okay, and then the standard deviation is 20%. So there is a change of 20 percentage points. That's the standard deviation, right? So a change from the mean of the Gini coefficient, an increase in two standard deviations. Oh, I'm sorry. That's the first part. So let's say that the Gini coefficient has this mean and this standard deviation. And let's say that the mean of the index of political stability is 49. Okay? 49 percentage points. Okay? So if we see or if we have an increase of two standard deviations in our independent variables, so if we move from this point to this point, so if we move from 40 percentage points to 80 percentage points, we're going to see a decrease in the index of political stability above the mean of the index of political stability, which was 49%, to below. Now it's going to be 30%. So it's going to be a huge decrease in this index. I hope you can, even if, of course, you have here the graph, so you can see the effects. But even if you don't have the graph, the mean and the standard deviation helps or should help you to see or to picture these effects in a more meaningful way. Okay? And remember as well that two standard deviations is what we can expect, the change that we can expect that happen in a variable that is normally distributed. Okay? If we say something like a change of 4 standard deviation, that's very uncommon to happen. It's very unlikely to happen something like that. What might happen is a change of 2 standard deviations. You can see most of the data revolves around those 2 standard deviations above and below the mean. So remember that's important to try to keep in mind in order to analyze these kind of results. Okay? Okay. This happened when we had an independent variable and a dependent variable. Sometimes the best type of independent variables are categorical variables or dummy variables. Dummy variables are those kind of variables that have to value 0, the absence of the category or of the phenomenon of interest, and 1, the presence of that phenomenon of interest, right? So those 2 states of the word are very easy to interpret in a linear regression context, okay? So let's say, for instance, that we have a second hypothesis. We say that democracies tend to experience higher levels of political stability than dictatorships. So democracy is going to have that value of 1 and dictatorship is going to have that value of 0, right? And in this case, we interpret the results as the difference between two groups or two states of the world, okay? Of the world, okay? So, and we can see here in the picture, in this plot, that the change is very significant or notorious. You can see that there is a huge difference between dictatorships and democracies. I'm sorry, dictatorships and democracies. And in this case, the parameter of interest, which is beta sub 2, is simply the difference between the two states of the world. So you have the value of democracies, which in this case is 61, minus the value of dictatorships, which in this case is 29, okay? So the beta coefficient is 32. How do you interpret that result? So you can say something like a change in regime type from dictatorship to democracy increases the political stability of a country in 32 percentage points. So if a country, I don't know, change its regime and liberalize its political system, allows elections and allow the participation and certain levels of dissent, you can see higher, or you expect higher levels of political stability, okay? Another way to interpret it is to say democracies tend to be 30% percentage points more stable than dictatorships. Both ways to interpret the results are correct. So this is the beauty of the categorical variables. They are easier to interpret sometimes than numeric independence. Okay, so if we want to choose between regime type or income inequality, so what is the variable that actually explains C? Remember that this is the question that we have related with internal validity, or when we are trying to explain the causal effect of a phenomenon of interest, we always need to rule out potential rival factors, okay? So in this case, the question is, which is the variable that actually explains why? Is X or is C? Remember that X is income inequality and C in that context was a regime type, right? Okay, so just to bring these ideas to your mind. So the linear regression is powerful not only because it provides a measure of the statistical significance and the magnitude of the effect of X and Y, but also because you can put in that formula, you can include in a formula as many rival factors as you want, okay? And in such a way, you have a powerful tool to at least cope with or at least tackle or address potential threats to internal validity. So you can control for different factors, not only one additional factor, but multiple additional factors and potential spurious variables, okay? So when we are in the context of multivariate linear regression, this is the formula. So you have a new parameter of interest that you want to estimate. You not only want to estimate beta sub 1, but you also want to estimate beta sub 2. And notice that we're modeling, this is called modeling, the effect of beta sub 1 and beta sub 2 as if they were, or as if you can add those effects, those individual effects, in order to explain why, okay? That's, to some extent, what we call the additivity assumption. That's another way to understand this kind of assumption. Okay, so just to keep working with this example, let's say that we said, okay, no, the political regime is the most powerful or is the actual explanatory variable. So now we're gonna say that our X is regime type, our Y is gonna be political instability, and we're gonna use income equality as the control variable. It's gonna be our C, okay? And remember that this was the result that we estimated with this relationship, between the relationship of regime type and the index of political stability, okay? When we control for C, or when we include C in the linear regression formula, what we are doing is to see what happened with the effect of X and Y when C is whole constant. What does it mean, whole constant, a variable in the context of linear regression? If you have a numeric control variable, you hold constant when you have that C variable in its mean value, okay? And if you have a qualitative or categorical variable, you're gonna hold constant C when you have C in its median value, okay? So let's say that we hold constant income equality in its median value. And the next question is, okay, is beta sub 1, remember that this parameter is the measure of the effect of X and Y. Does beta sub 1 remain statistically significant after we hold constant C? Okay. If not, we should see something like this, right? This was when we only had X, and this is the formula when we have X and C. If we have something like this, and this is not statistically significant, then we need to reject our hypothesis because the relationship was spurious. So it was artificial, and the inclusion of C helped us to see that this was artificial, that this was not a real effect of X and Y. That was caused by something else that in this case was C. Okay, so that's what happened when the relationship is spurious. If the effect of X and Y is still statistically significant, what we need to do is to examine the substantive effect or the substantive significance of this relationship. And you should see something like this at least. Next question that you need to answer is, did the sign of the effect of X and Y change? So remember that we had this, the sign of the effect here is positive. And if the inclusion of C doesn't change the sign of the effect, probably we have an additive relationship, right? And both variables help us to explain why. If you see something like, if, I don't know, if the blue line is, I don't know why, negative, which means that democracies tend to be less stable than dictatorships, there might be happening something else. Maybe there is an interaction effect between X and Y, or something else is happening and is explaining these effects. Because the effect of X is still statistically significant, but the sign of the effect changed. We suspect that there is an interaction relationship between X, Y, and C. We need to model that kind of interaction effect. And we do it by actually writing the formula, that conditional effect, okay? So let's return to hypothesis 1. Let's say that we are trying to explain again income inequality and political stability. Okay, no, I'm sorry. That we want to explain political stability with income inequality. Income inequality is our independent variable, and we're going to use another control variable. Let's say that that variable is the presence of oil. A little bit of notation. What you do is, what I mean is, when I said that you're gonna model that conditional effect, is because you actually gonna write in the formula this new this interaction, and the interaction is modeled with a multiplications between X and C, and also the parameter that you want to estimate here is this one, is beta sub 3. And notice that these new terms included in the function are modeled as additive, okay? So you're gonna add beta 3 to beta 2 and to beta 1. Okay? So that's important to keep in mind. Okay, so why did I change the hypothesis again and use again a dummy variable as C? Because it's very easy to explain this conditional effect. If zero takes the value, if C takes the value of 0, so you don't have anything here. But if C takes the value of 1, you have the value of X here. Okay, that's going to be important for the analysis. So it's mathematically difficult to interpret, but it's graphically is very easy. You should see something like this, for instance. When C is 0, maybe you can see something like this. Maybe there's no effect. And when C takes the value of 1, so when there is presence of oil, you can see a stronger negative relationship between inequality and the index of political stability. In other words, imagine a country that has that is a lot of wealth, economic wealth, because there's oil, but there is a lot of inequality. Okay, maybe we can expect that the levels of political stability will be higher than in countries where maybe there's no there is inequality, but there is no real I don't know, economic development or something like that. There's inequality, but it's not gonna be as intense as in the case of when there is this wealth in the country as this imaginary country with oil or something like that, where oil is all the revenues of oil are concentrated by a corrupted elite or something like that. In that kind of cases, we can expect higher levels of political instability. Okay, so for instance, in this case, we can say and we can interpret that income inequality only has a statistically significant and negative effect on political stability in the presence of oil. That might be our interpretation. Okay, so I have said many times that linear regression is very powerful, but of course it has limitations as any other inferential method. Okay. The first limitation is that you can only use linear regression with categorical. Oh, that's a mistake. You you can only use it with numeric dependent variables. So what do you do when you have an ordinal variable or a nominal variable as your outcome of interest? There are other methods, but more advanced methods that actually are based on the linear regression. And there is a family of methods called the generalized linear models that use the foundations and the principles of the linear regression, but adapt those principles to the context of other types of dependent variables. The second limitation of the linear regression is that when you have this possibility of include multiple control variables, maybe you don't you just include as much as you can. And I have seen regressions with 30 variables, explanatory variables, or things very large and very difficult to interpret. But this comes at the cost of reducing the degrees of freedom or the prediction capacity of the model. Sometimes you don't have like 5,000 observations or something like that. Imagine that you are studying the United States, the states of the United States, for 1 year. So you only have 50 observations in your dataset. If you include 30 variables, you're going to have very low degrees of freedom, and probably you're going to have problems estimating the model. Okay, that's probably the best example to illustrate this kind of limit. And the final limitation is that if you don't have an actual research, experimental research design, you're still gonna have problems of all other types of observational studies, which means that there might be other factors that actually explain uh, your variable of interest. So you cannot rule out all the potential factors. You cannot include all the variables in one model, right? So that's important to keep in mind because the linear regression also has that limitation. But you can say at least that you try to control as much as you could for the most important variables. Okay? Okay.